Well, then we are going to see in the electronic board everything we have been describing about how the fan works and how its speed is regulated. Well, we turn on the light, and now, please observe this part of the circuit, of which we have it very clear. Here we have the dephasing capacitor of 1.2 microfarads. This can also be the reason for failures if the fan does not turn well. It is removed and a new one is placed to test it. And we have here the circuit we were mentioning. Well, as this speed is regulated, we need an optocoupler because the integrated circuit has to tell it at what speed to turn. So, we need an opto to make a dielectric division, that is, so that what happens on this side does not affect the microprocessor, and it does not get burned by the high voltages that are handled here. So, let's observe the following. Here are pulses generated at the moments when they have to turn on. The Optotriac is powered, which connects from the other side. And there is where then, through this resistor, a low voltage is injected at this point of the triac, and the triac will do a connection. Look at this side. Here we have the line, and here we have the neutral. Here we have the line. And the line will feed this point of the triac. This line will also come here, through this resistor to reduce that voltage a bit. And when this point is connected, thanks to the fact that this light turns on, this terminal of the triac will be fed, which will allow these two to connect, and the middle point of the fan will be fed, which will be the common. At the same time, on the other side, we have the neutral that feeds the working coil, and through the capacitor that is in this rectangle, the starting coil is fed. And this is where the cut and the on are produced, those 100 times per second, constantly. What elements can be damaged if this does not work? Any of these. That's why we're going to check them one by one. In the case of resistors, we will check their resistance value. In the case of the optocoupler, we will be testing the lead and also the other area of the circuit as we have done previously. And in the case of the triac, we will be testing directly that there is no short circuit between the two gates, or rather, between the two sources. Well, then we are going to check it in the following way. We place the multimeter in resistance position and we are going to measure from the side of the triac. We are going to measure it from the other side. We have to have a high resistance of megohms to know that everything is fine. There it is. Let's try it this way. And then we have a very high resistance that even goes to open line at this point. We are fine, we are with open lines. Now, testing towards the one that energizes to activate, we will have a resistance, which is derived from resistors that we have placed here. These resistors are in good condition, 500 ohms and 100 ohms. And here we have the optocoupler, which we have to test its light side and its opposite side. Remember that the light side we will test in diode mode. And there we have the voltage drop of a lead, 1.12 volts of drop. We are going to invert and we have the voltage drop of the diodes that are on the opposite side, forming part of the variable voltage circuit, which are the ones we have in the driver that is the one that will energize it. Very well, this is how we are testing all the components of this voltage variable circuit through the wave cut, based on a zero crossing detection. Any problem in the zero crossing detection, what we will have is a fan error. It will not work, it will mark an error, or it will tell us directly the plaquette. If it is more sophisticated, it will tell us zero crossing detection error. This is how the speed of these fans is regulated. This is the way it is done electrically, and we can measure the components without voltage, as we are doing now. And we can also measure this with voltage, as we are going to do. Well, to measure this with voltage, what we have to do is place between the neutral and the line that is the one that comes from the triac. Between the neutral and the line, we have to place the multimeter in voltage and alternating current, since it is an alternating current of 50 Hz or 60, and this will mark us a certain average voltage. These voltages will vary depending on how many electrons are sent, and what a multimeter will do is to take an average. So, as a result, what we are going to see finally, controlling voltage between this point and this, which remember that here is cut through the triac to this power. Between these 2 points we are going to be finding, in low speed, a voltage of approximately 167 volts. In medium speed, approximately 185 volts. In high speed, approximately 205 volts. Always talking about 220 volts, what a multimeter will do and take an average, and since the wave is being cut, it will believe that the voltage is lower. In reality, the average voltage or the force that is sent to it is lower. This would be the voltage test. Remember that you will find these circuits in conventional ones, in most of them currently, and in inverters you will find them in many, especially those that are 9,000 or 12,000 BTU, or in Fragorias, we are talking about 2,250 or 3,000. Very well, one more component that I want to mention is that, sometimes, instead of an optocoupler that feeds a triac, which allows 220 volts to pass. Here we have an optocoupler, and here we have the triac. Here, instead of finding these two components separately, you can find them together. When you find them together, we are talking about an optotriac, and, in that case, we are talking about a component that has a LED on one side, and on the other side we have a gate that allows the passage of 220 volts. They can also be found in this way, and the component encompasses all of this. Always to be able to identify these components and know how to measure them, remember to look at their patent. In other words, remember to observe the number that it has on its component. In this case, we have a Mach 3021. Well, this is an optocoupler. Perfect, then I will show you a plaquette that has an optotriac. On this plaquette, we are seeing directly a power supply from the microprocessing area, and through these tracks we go directly to this component, which feeds this LED, and on the other side, directly, allows the link of the 220 to power the fan. Notice that directly from the LED, right there is where the 220 pass through and power the fan through this connector. Here we have then an optotriac. Here we have it all together, all assembled. Okay, so far with the way to regulate the speed in these fans. Is there anything else? Yes. How does the electronic board know how fast the fan is spinning? This function is not fulfilled by these 3 power cables, but by the 3 additional ones that you often see. They are a Hall effect sensor. Through these 3 terminals, the board knows how fast the fan is running and sends it more or less electrons through the circuit we just analyzed. In the next video, we will talk about the Hall effect sensor and how it works. Please leave a comment if you have any questions.